Okay, this is chapter 22, Organic Chemistry, and this is part of my Gen Chem 2 class. Normally, organic chemistry is not touched upon at all in general chemistry because most students go on and take Orgo 1 and Orgo 2. But for those students that were taking the AP chemistry exam, they had to review their organic and nuclear for that exam. So this is just a brief review of the intro to organic chemistry. So alkanes are hydrocarbons. Well, first of all, let's talk about what a hydrocarbon is. A hydrocarbon is a compound that contains only hydrogen and carbon. And there are three different classes of hydrocarbons. Alkanes is one of them, and they have only single bonds. And then you also have alkenes, and they have a double bond. And you have alkynes, which have a triple bond. If you recall from Regents Chem, alkanes have the general formula CnH2n plus 2, and alkenes have the general formula CnH2n, and alkynes have the general formula CnH2n minus 2, where n is equal to the number of carbons. These are the selected properties of the first 10 normal alkanes. These are your prefixes over here. If you recall, meth is 1, eth is 2, prop is 3, but 4, pent 5, hex 6, hep 7, oct 8, non 9, and dec 10, which you can see by looking at the general formula. You can see as the number of carbons increase, the molar mass increases, and you can also see as the number of carbons increase, the boiling point increases. So as carbons increase, the boiling point increases. And this is because you have a larger molecule and it's going to take more energy to pull it apart. One other thing that I want to mention right here also is that if something is saturated, it contains all single bonds when we're talking about these hydrocarbons, and if it's unsaturated, then that means that it contains a multiple bond, as in a double or a triple bond. What is an isomer? Well, to review, an isomer is something that has the same molecular formula but a different structural formula. So as soon as you take the structure and you arrange it differently, it has new chemical and physical properties, and therefore a new name. So let's look at butane. Sometimes when it's the normal structure, you'll see an N-butane. That just means regular butane. But tells us that it's 4 carbons. The ane tells us that it's all single bonds. So this is going to have the general formula C4H10, because the general formula for an alkane is CnH2n plus 2, double the carbons plus 2. Now if I want to make an isomer of this, remember you're going to take an end carbon off. So an end carbon is called a terminal carbon. You're going to take that off and you're going to put it in the middle of the chain. You don't want to take it off and put it on the end, because then all you've done is bend the chain. You actually haven't created a new structure. So an isomer of this could be like this. And this actually has two names. This can be called 2-methylpropane, or it can be called isobutane. Now remember, when we're naming, you want to number the groups so that the branch or the functional group has the lowest number. So let's review and draw some isomers of pentane. You need at least 4 carbons in order to create an isomer, so that's why I gave you the first example with butane. The more carbons you have on the parent chain, the more isomers you can draw. So we know pentane's got 5 carbons. 1, 2, 3, 4, 5. I put my H's. The general formula is C5H12. And I'm going to take a terminal carbon off, and I'm going to move it here. And I'm going to take another carbon off, and I'm going to put it in the middle. And that's all we can do with this many carbons. So the first one is normal pentane. The second one, our parent chain is now 1, 2, 3, 4, and it's all single bonds, so it's a butane, and on the second carbon I have a methyl group, so this could be called 2-methylbutane, or it's also known as isobutane. And the last one, I've got 3 in my parent chain. It doesn't matter whether I count it left to right, north to south, it's still going to come out the same. So now I have 2 branch groups. They're both on the second carbon, so this is 2,2. Because the groups are both methyl, I need to use the prefix di to tell me that there's 2 methyl groups. The 2,2 is the location, and it's going to be propane because it's 3 carbons, all single bonds. This is, I don't know what I did over here. I have a triangle. This should be also known as, sorry, and this is also known as neobutane. Okay, reviewing the rules. You number the longest chain of hydrocarbons. Find the longest continuous chain. Don't backtrack, don't lift up your pencil, longest continuous chain, and then number the chain so that the branches have the lowest number. Identify the branches by a number followed by a comma, and then name the longest chain. Now if you only have one, then you can just put a dash between the number and the name. If you have multiple numbers, then you put the commas between the numbers. So let's look at some examples. In this one, my longest chain, if I go north to south, is only 3. If I go left to right, it's 4. So 1, 2, 3, 4. I see that I've got methyl groups on the number 2, so 2, 2, and it's going to be dimethyl because there's 2 of them, and the longest chain is but, and it's all single bonds. You had 2 of those of the same one on your paper. Over here I have 1, 2, 3, 4 as my longest, and I have a methyl group on my second, so this is 2-methylbutane. And over here, very interesting, I've got 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. No matter how I count it, I've got 4. I have a methyl group on 2 and 3, so this is 2,3-dimethyl butane. Let's talk about some functional groups. Remember, a methyl is only 1 carbon, and ethyl is 2 carbons off the parent chain. Propyl is 3 carbons off the parent chain. You won't have to worry about so much in this class the isopropyl or the butyl or a sec-butyl or an isobutyl. You'll get into these when you actually get into organic chemistry. Alkenes have at least one, I went over this, double bond, and alkynes have at least one triple bond. Number the longest chain of hydrocarbons, identify the branches placing a number followed by a comma, name the longest chain. If there is a multiple bond, meaning a double or a triple, identify the bond by indicating the carbon number that the bond occurs at. Number the molecule such that the double or triple bond gets the lowest number. So this is important because if you have bonds present and branched carbons, you're going to number the bonds so they get the lowest number over the branches. Let's take a look at some examples. So here I have 1, 2, 3, 4. So I've got 4, but I have a double bond. So this is just normal butene. I could just write butene. I don't have to state the number of where the double bond is because it's on the first carbon, which makes it normal. Over here I'm going to number from right to left. 1, 2, 3, 4, 5, 6. And I've got a triple bond, so this is just normal hexyne. In the bottom one here in the middle, I've got 1, 2, 3, 4. Now you see I've got 2 double bonds. This one's a little bit different. I've got one on the 1, comma, I've got one on the 3, and I know that it's 1, 2, 3, 4 carbons, so it's going to be butane, but I'm going to drop the E and it's called butadiene. The di for the 2 bonds comes in the middle of the word, right before the E ending. So when you have multiple double bonds, okay, you're going to put the di right before the E ending. Over here I've got 1, 2, 3, 4, 5. So I've got a double bond on the 1, which I don't have to worry about naming that, and I've got a methyl group on the 4. So this is just simply 4-methyl. It's pent, and it's ENE because there's a double bond. Down here I've got 1, 2, 3, 4. Continuous chain. Again, I've got a double bond on the first carbon, but I've also got a methyl group on the second, so this is 2-methyl butene. And in the bottom one, 1, 2, 3, 4, 5. I've got a double bond, a triple bond on the second carbon and a methyl on the fourth carbon. So this is 2-methyl. I need to say where that triple bond is because it's not on the first carbon. 2, and it's 5 carbons, pentine because it's a triple bond. Okay, something new that we really didn't learn in Regents chemistry is the difference between cis and trans isomerism. The difference between cis and trans is where the branch groups reside. So In Cysts, your branched groups are on the same side. And in Trans, the branched groups are on opposite sides. So here you can see you have cis-2-butene, okay? And the way it bends, the terminal carbons are on the same side. Here in trans-2-butene, they are on opposite sides. And this is caused by what's called the steric strain, which is restricted rotation due to the presence of the pi bond. It gets a little bit more involved in that, but at this level this is a good enough understanding. Let's do a couple of more examples. Here, if I were to draw this, so here I have cis-1,2-dichloroethene, cis-1,2-dichloroethene. And if I drew it like this, oh, I put too many carbons here. There we go. I have trans 1,2-dichloroethene. And just to give you another look at the way something appears, I can draw cis-3-hexene and trans-3-hexene. So I can do a partial condensed formula here. So CH2, CH3, CH2, CH3. So that's your cis and then your trans. There you go. Okay, let's briefly talk about aromatic groups. Aromatic groups are carbons chains that have been connected to form rings. The most common one is your benzene, and this is missing the double bonds here, so let me put them in. There should be a double bond here, a double bond here, and a double bond here. So this is one way of drawing benzene. This is another way of drawing benzene. These are actually resonance structures of benzene. And that's because in one you have the double bond on the 1, 3, and 5, and on the other one you have the double bonds on the 2, 4, and 6. And this, believe it or not, is the usual representation. They put a circle in the middle to represent the delocalized electrons. So any of these are appropriate structures for benzene. Something new that I want to talk about down here. These are just showing you more complex aromatic systems. And this is a really bad picture. In your book, it's table 22.3. This picture's on the same page. I would look at it. But what you see here, you have P's and O's and M's in front of this. Okay, so here we have P-dibromobenzene, and here we have M chlorobenzene, and then down on the bottom I believe we have para. Oh, this one's para. Here's meta dibromobenzene. Let's talk about the difference between ortho, meta, and para. So ortho, which would have an O in front of the name, is when you have your branch groups next to one another. And they don't show any ortho in this picture. And then you have meta, which is an M, which means that they're next to one another with a carbon in between. The branch groups. So that would be this one right here. Or 1,3-meta dibromo. This is this one right here. So this is an example of meta. It's 1,3-dibromobenzene. And then we have para, which is a P, where the branch groups are opposite one another. So in the one next to it, you have P-dibromobenzene. This is your P. Branch groups are opposite. Okay. And here in this beautiful one we have 1-methyl followed by 2, 4, 6 tri-nitro. The NO2 is nitro, and this is a benzene ring. Okay. Most of these should be a review. The common functional groups: halocarbons, chloro, fluoro, bromo, iodo, alcohols, an OH ending on the end of the carbon, ethers, an O in the middle. The difference between aldehyde and ketones: aldehydes have the double bonded oxygen on the end carbon, ketones have the double bonded oxygen on an interior carbon. Your carboxylic acids, also known as your organic acids, from what you remember from Regents Chem, has a C double bond O OH at the end. And then your esters are the result of an alcohol and organic acid combining to form an ester. So you have the C double bond O O in the middle of the group, and your amines are NH2. So let's look at a couple of examples. Right here you see the functional group OH. Your clue that it's an alcohol, 2 carbons, so it's ethane, drop the E, OL, ethanol. Over here you have a double bonded oxygen on an end carbon. This is going to be an aldehyde, so it's butane, drop the E, AL, so butanol. Over here you have an alcohol on an interior carbon, and you have a methyl group. So I'm not going to ask you this, but this is actually considered a tertiary alcohol because it's got an alcohol that is attached to a carbon. Right here, the OH is attached to a carbon, and that carbon is attached to 3 other carbons. Okay? If this wasn't here, the methyl group on the top, then it would just be a secondary alcohol because the OH is attached to a carbon with it's attached to 2 other carbons. So this is a tertiary alcohol, and this is going to be 2-methyl. You have to tell me where it is, 2-propanol. So you got to tell me where the OH bond is. And on the one up here, we have an aldehyde also with a methyl group. So this is going to be 2-methyl propanal. Okay. Here I have a double bonded oxygen and I have an NH2 group. So this is an amine, 2 carbons. So this is ethanamine. Here I have the COOH ending. It's an organic acid. So this is ethanoic acid. Here I have a COO in the middle. That's my ester. Remember with the ester, the last part of the name comes from an alcohol with a YL ending. The first part of the name comes from the organic acid with an O8 ending. So this is going to be ethyl, came from the alcohol, 1, 2, 3 carbons, is going to be propanoate. Over here I have another ester. I have 3 carbons, YL, 4 carbons, O8. So this is going to be propyl butanoate. And my last one over here, this is a benzene ring with a acid functional group, so this is benzoic acid. Okay, that's a review of organic chem. Please look for the new problems posted on Schoology. I said that this unit was to be determined. I will post them today.